Good afternoon, everybody. Rajashri sir, our honorable speaker, Dr. Shunipa Roy, madam, are already joined with us.
Yes, sir. Yes, sir.
We wait 2 to 3 minutes, then we start our today's sessions.
Okay.
Rajashri sir, uh, Rajashri sir,
Yes, sir.
I am audible, sir. Sir, please start the sessions.
Okay. Shall I start then? Okay.
Yes.
Okay. Okay. Very good afternoon to everyone. Myself, Rajashri Chakraborty, Assistant Professor, Department of Mechanical Engineering from GKCM College, as well as I am the joint co-convener of this event. A very warm welcome to all of you. Our third day of this FDP. Today we have our honorable guest and speaker, Professor Dr. Shunipa Roy, Madam. Before we start our session by Shunipa Ma'am, I would like to give some small introduction about Ma'am. We are very much privileged and honored having Dr. Shunipa Roy, Madam. Madam Shunipa Madam received her PhD degree from Jadavpur University in Electronics and Telecommunication Engineering Department in 2024. She is presently serving as Associate Professor and Head of the Department in Electronics and Communication Engineering at Guru Nanak Institute of Technology, Kolkata. She is the recipient of National Scholarship from Government of India, Junior Research Fellowship from DST, Government of India, and Senior Research Fellowship direct from CSIR, Government of India. Her current research interest includes nano device, graphene, supercapacitor, and gas sensor. She has more than 40 publications in high impact factor journal and CPD credited conference publications. She is the author of 3 books of international publishers like CRC Press, Bentham Science, and owns several book chapters of internationally reputed publisher. Dr. Roy is the senior member of IEEE, Secretary IEEE CASS Kolkata section, and published several patents. She is also the regular reviewer of IEEE transaction on nanotechnology and many journal of repute. She has been invited as an invited speaker in several national and international programs and chaired the session of many sponsored international conferences. Dr. Roy is the principal investigator of several funded projects and supervising many doctoral theses at this moment. So we are very much delighted to have Madam. Once again, we must say this. And we are handing over the session, Dr. Shunipa Roy, Madam. Madam, you can start. Madam, are you ready?
Everybody.
Yes, ma'am. Yes, ma'am. Thank you, ma'am.
Okay, Principal Madam, Rajasri sir, and all the organizing committee members for providing me the opportunity to present my research in front of you. I'm sharing my slide. I hope it is visible.
Yes, ma'am.
Yes, ma'am. Yes.
So today my topic is particularly gas sensor, that is graphene based. How it is work on how graphene works on sensor environment and why people are choosing graphene, because there are so many semiconductor material and so many gas sensing material is there. Still, we are inclined to graphene nowadays, and the total research has been shifted to search that find the advantages of graphene. So to start with, fabrication of sensor is not so easy. Fabrication of sensor is not so easy. So to start with graphene-based sensor, we should know how the sensor works actually, because all of you are not belong from the similar field, and maybe you are not having any idea how gas sensor works. So I am starting with that first. So I have so many slides. Actually, I have ready slides, and I am not actually not cut and paste all these things. I'm not doing. So I may skip the slide that is not feasible to you or beyond of the scope of this topic. So first is there are so many deaths in the coal mines in India due to the presence of methane. And approximately 50 numbers of methane sensors are needed per coal mine. So overall sensor requirement in India is huge, but not that much technology, particularly foundry system is missing in India. So Government of India now going to develop some foundry system, that is the mission, National Semiconductor Mission, NSM. Government of India has taken the initiative, great initiative. So this type of sensor, all this manufacturing could be possible in India within few years. So as we need lots of sensors, so while fabricating sensors, we should know what are the limitations, what are the matters we should look for. First one is temperature, operating temperature. Second one is power consumption. So power consumption, not only for sensor, everywhere in our household also, we always seek for power consumption because we check that whether it work on low power or low wattage is there or not. So low power dissipation is the prime criteria while we are selecting the gas sensor. And also there shouldn't be high operating temperature, because if the operating temperature is high, then battery will consume very fast. So that should be avoided. So large power dissipation can be considered greater than 1 watt, and high operating temperature can be considered as greater than 300 degrees Celsius. So low power device means at least less than 100 milliwatt we can consider as a low power device. That is not particularly MOSFET, because MOSFET, etc., is the power consumption is very, very less. It is less than 1 milliwatt even. But for this type of device fabrication, we will consider only less than 100 milliwatt power consumption. So you should keep in mind that we need operating temperature, not high for this gas sensor material, gas sensor. It should be at least 100 degrees centigrade temperature, less than 100 degree or less than equals to 100 degrees centigrade temperature could be considered in this nanotechnology domain. So these 100 degrees Celsius temperature, who will generate this temperature, how we can get this temperature in a particular device, that is the point of question. Because when you are handling a device, that is obviously battery operated. So there may be a 9-volt battery, 9-volt battery. So if the power consumption is huge, then, and if you have to go to the for the field work, say you are carrying the device, carrying the instrument, and this 9-volt battery could consume in 2 days. That is not possible. So this sensor, this gas sensor particularly, we carry in coal mines, etc., in many hazardous area, that is remote area. So it is not possible to carry junk of battery in our packet and go with that sensor material. It is not possible. So we should keep in mind, we have to develop a low power consumption device. So this is less than 100 degrees Celsius. So who will generate this temperature? We will discuss later. So to circumvent this type of problem, the sensing temperature, to reduce the sensing temperature, first and foremost thing is we have to shift to thin film. What is the difference between thin film and bulk material? Bulk material, say you are taking graphite. Graphite, if we exfoliate it or if we cut the layer one by one, you will get graphene. So graphite is the mother, graphene is the child. So the thing is that when you consider a bulk material and we consider a thin film of same material, the characteristics are totally different. The electronic properties, optical properties, mechanical properties, etc., totally different, though the mother and child belong from the same category. This is the characteristics of thin film. So we have shifted to nanocrystalline material. So that nanocrystalline material is very miniaturized structure in the order of nano domain, 10 to the power minus 9. And the power consumption is very, very less. And we are also using to reduce the power consumption of the device that is less than 100 milliwatt. We should move to the MEMS technology. So what is MEMS? I'm going through. And this low temperature requirement, we have to build micro heater. So heater, we are comfortable with heater in our household. Many of us keep heater in our kitchen. But micro heater and heater, the difference between that, in our household, the heater we are using, that is a very, very long wire and it is twisted. But in micro heater, the length of the wire is of the order of micron and the thickness of the wire is of the order of microns, like 50 micron only, 20 micron, thickness of the wire. And the length of the wire is roughly 1000 micron. So this is very difficult task to fabricate the micro heater, and for that we have to follow so many processes. If we don't follow the processes, we will not be able to develop flawless micro heater structure. It will cut, otherwise it will be broken and it will not generate the temperature, because broken micro heater means there is no continuous conduction. So micro crack, this is called, this broken I am telling, but technically we call it micro crack generation. This micro crack generation is very, very prone to, because the sensor we are keeping not at home, not in Almira or not in a safe place. The sensor we are putting it in a hazardous area, open to environment, in some cone mines, and where dust, pollen, etc., rainwater, everything is there. So this micro heat, obviously my heat, that is sunlight, everything is there. We put the sensor in that place to sense the hazardous gases. So the thing is that we have to make it rugged, and we have to try that micro crack generation could be avoided. So now the thing is that first we move through the microelectronics fabrication part. Let us start with the MEMS technology. What is MEMS? MEMS is nothing but the microelectromechanical system. So the name suggests that it's mechanical system. So mechanical means there is a concept in our mind. Mechanical means something is moving, something is rotating. But always that is not true. This MEMS technology we are implementing in the sensor, in fabricating the sensor, that is not using any movable material, movable parts. The thing is that the technology that is used to fabricate MEMS, the same technology we are using to fabricate our sensors. That is, this is called MEMS-based sensor. So this is particularly MEMS. MEMS is totally depends on micro machining. Micro machining, this is an example of micro gear or micro gear. This picture I am showing you. You can see how the structure has been formed. This is obviously of the order of micron level. And this structure, the one and only way or method that we can adopt to fabricate this structure is micro machining. So next, I am skipping some slides. So the target of our MEMS is response time of the sensor is very small. The miniaturized device, very, very small device can be fabricated, higher sensitivity, reduce thermal mass of the device for this using this MEMS technology, and power consumption can be scaled down. So again, I am telling 3 key points. That is small size of the device, batch processing using VLSI technology. That is, batch processing means at a time, if we need hundreds of sensors, we don't have to wait 100 times fabrication process. We have to go through 100 times fabrication process. Take a silicon wafer and make 100 sensors at a single time, same time. So this is the point. This is called batch processing. Integrability, that means sensor and the signal conditioning unit could be integrated on the same chip. That is one of the greatest advantages. So here you can see the MCQ, but this MCQ could be shared by the organizing committee also. I am skipping this slide. So now the silicon, this MEMS technology, now the term you should be familiar with it, that is CMOS compatible. What is CMOS compatible? CMOS compatible means the device is fabricated on silicon. So why silicon? Because silicon is very inexpensive material. Silicon could be fabricated, prepared from sand. Sand is raw material that is available in the nature. It's free of cost. So we don't need to purchase the raw material, at least from the third-party vendor. So that is the thing. It is available in the abundant in the nature. We can take silicon, process it, and fabricate the silicon wafer. We can take sand, process it, and fabricate the silicon wafer. So silicon, obviously, very good material. This is a little bit brittle, but hardness, Young's modulus is very, very high. So next is, I have mentioned that batch processing. So this is one of the example of batch processing. See, sorry, I have to. So this is the batch processing technique. See, using a single wafer, how many devices can be fabricated? So this is the silicon ingot, silicon wafer. After cutting this ingot, we are getting silicon wafer. That is roughly 300 micron thick silicon wafer, and the thickness is 2.5 inch roughly. It may vary, but generally we take this sized silicon wafer, and the method we follow to fabricate the silicon wafer, that is Zoralski method. So the total, this is called ingot. The right hand side part that we can see, that is ingot. And that is totally this one, that is ingot, and that is totally fabricated from sand. There are some process obviously involved with it, but the raw material is sand. Now, so first thing is, after having the silicon wafer, you know silicon is the semiconductor. It is not conductor, it is not insulator. Semiconductor at room temperature. But if you increase the temperature of the silicon, one time reach, it will behave like the conductor. So what will happen if the temperature of the silicon wafer will rise? And on top of silicon wafer, obviously you are going to fabricate some device. So if the temperature of the silicon wafer raised, what will happen? This will become conductor, and the device that is fabricated on top of silicon wafer, that silicon and the device will get shorted. Short circuit will be there. So it will damage the whole device. So for that reason, we have to deposit silicon dioxide on top of silicon wafer. What is silicon dioxide? Silicon dioxide is nothing but a very good insulator. There are so many good insulators available in the market that is silicon nitride is much better insulator than silicon dioxide, but still research is inclined with silicon dioxide dielectric. Why? Because silicon dioxide is very easy to deposit, whereas silicon nitride fabrication is high-end laboratory is required, and it is not so easy task. So research is inclined on the silicon dioxide dielectric. So take the silicon, on top of that silicon dioxide layer, you please deposit. So there are two types of oxidation process. First one is dry oxidation, another one is wet oxidation. Dry oxidation means, as the name suggests, there are no water molecules involved. For wet oxidation, as the name suggests, some water molecules are involved. For dry oxidation, we are using just silicon and oxygen. That is enough for dry oxidation. But for wet oxidation, we are using silicon, oxygen. With that, we are, carrying, we are inputting some water vapor inside the chamber, oxidation furnace. So you see, as the number of oxygen molecules are more in wet oxidation process, because we are water molecules are getting added with it. So that is the thing. Wet oxidation is much faster than the dry oxidation, as the number of oxygen molecules are more. So why people are still working with dry oxidation process? The thing is that in dry oxidation, the surface finish is smooth, but it takes longer time. Whereas for wet oxidation, surface finish is not that type of smooth that is observed in dry oxidation, but the process is faster. When we have to fabricate the device, we have some deadline, we have to fabricate the device within some deadline, don't have much time, then we should go through wet oxidation. And wet oxidation, obviously, there is a compromise. Whether we choose dry oxidation or wet oxidation, it depends on the requirement totally. So these are the few fabrication steps, that is cleaning, deposition, etching, and patterning. So first we go through cleaning, because device cleaning is not so easy task. So why cleaning is required? Because there are so many contaminants available in the weather, in the atmosphere, in the ambience. So what are these type of contaminants? Dust particle. The micron level dust particles are present in the air, what we cannot see with naked eye. So there are so many oil and grease are present. We can't see naked eye. So these type of contaminants are always present in the air. So method of cleaning, if we follow, there are two types of cleaning, like oxidation, that is wet cleaning, and dry cleaning. Wet cleaning, obviously, we using water, and for dry cleaning, we are not using water. So dry cleaning, we need a big setup where the cleaning, the external foreign particle that is attached with the silicon wafer could be removed from the wafer surface. That is the part of the dry cleaning. And wet cleaning is the wet process, where we are using water. So what are the difference between wet cleaning and dry cleaning? When people choose wet, when people choose dry? So dry cleaning, high-end laboratory is required. There is a financial constraints. Those who are capable to establish the setup, well and good. But wet cleaning is less expensive process. Wet cleaning is less expensive process. In our laboratory also, we can do this wet cleaning process very easily. So it depends on the requirement and also some conditions. So wet cleaning means you can take sulfuric acid, you can take hydrochloric acid, etc., with some added water and with hydrogen peroxide. It is using actually as a buffer solution. If we use hydrogen peroxide, buffer solution. Buffer solution, what is the function of buffer solution? Buffer slow the process. The process getting slower when we use some buffer solution due to some chemical reaction. So the thing is that, so there are some metallic impurities, so many calcium, cobalt, copper are present. There are so many slides on cleaning method. So this is the summary, because this is not beyond of our scope to present all the detailed study in this lecture. So if you carry the silicon wafer and put in trichloroethylene, first boil and then put 3 minutes in ultrasonic cleaner, it will remove the organic compounds and also dust particle. And step 2, if you put the silicon wafer into the acetone, it will remove oil and grease. Step 3, if you take the silicon wafer and put in the sulfuric acid, it will remove the sample clean in DI water. And to remove inorganic compounds from the wafer surface, we use ammonium hydroxide. And to remove hydrochloric acid from the sample, we use some, to remove the alkaline organic compounds from the wafer surface, we are using hydrochloric acid. So these are the summary. Now, the thing is that this is very interesting. What is clean room? Because while the microelectronics fabrication is being carried out in the clean room. So what is clean room? A clean room is a controlled environment where pollutants like dust, airborne microbes are filtered out in order to provide the cleanest area possible. So this is the class of clean room. I mean class 1, class 10, class 100, class 1000, class 10,000, class 1 lakh. What is that? It is written over there at the bottom of the table. See, a class 100 clean room, for example, would not contain more than 100 particles bigger than 0.5 micron in a cubic foot of air. So 0.5 micron foreign particle should not be there in number of 100, more than 100 in a, if we call it class 100 clean room. And the area, volume of the air is 1 cubic foot of air. So class 1 clean room means one particle bigger than 0.5 micron should not be present in the 1 cubic foot of air. So hope you understand, or hope you assimilate that class 1 clean room maintenance is very, very costlier process rather than class 10,000 or class 1,000. Because once you the setup of clean room is complete, that is not the end. You have to maintain the clean room. So for the maintenance of this clean room, what should we do? There are so many HEPA filter. It's a high efficiency particulate air filter, ultra low particulate air filter. You have to incorporate inside the clean room, and outside air is first circulated through a filter system. So this is the picture of the clean room I have collected from the web. And the particle counter we need to maintain the clean room. There are so many devices we need to maintain the clean room. What is the particle counter? The formula is NL equals to root over A. NL is the number of particle measuring points, and A is the area of the clean room in square meters. I mean, clean room, the area say 100 square meter if the area of a clean room. Then number of points where you have to measure checkpoint. Point means checkpoint. Number of checkpoints you should measure the clean room, whether it is maintained or not, that is equals to 10. Root over of 100 equals to 10. I mean, in a 100 square meter room, you have the checkpoint should be 10 for the maintenance of clean room. So this is the particle counter, that is one is handheld and another is bulk. So all these are present in the market, available in the market. So there are so many things, not only particle, humidity, pressure, temperature, all should be maintained to the point in a clean room. For that, we need different types of devices to maintain the clean room process. This is very costlier process, that is in India particularly, this type of clean room is not available. Now I am ignoring the MCQ, organizer will provide you. So silicon micromachining. There are two types of micromachining. First one is bulk micromachining. Second one is surface micromachining. So bulk micromachining and surface micromachining, one is called subtractive process, another one is called additive process. So just a minute. Micromachining. Okay. Is there any question, madam? Also, the upper figure is the example of silicon micromachining, bulk micromachining, and the lower figure is the example of surface micromachining. Here we can see why this is called subtractive process. The gray colored material is nothing but silicon, and through bulk micromachining technology, we are removing the silicon from the bulk counterparts. So as we are subtracting silicon from the bulk silicon wafer, that's why this is called subtractive process. Whereas surface micromachining called additive process, because we are taking silicon substrate we deposit the, anything SiO2 layer or any photoresist layer, say this is a SiO2 layer. Then on top of that, a polysilicon layer or any metallic layer, maybe gold, maybe platinum, any metallic layer can be deposited. And if you put the wafer into the hydrofluoric acid is good etchant of silicon dioxide. Silicon dioxide will be etched out, and the resultant structure you will get that this one. This one will be your resultant structure. As we have started with silicon wafer, we are ending with this additional structure. That's why this is called additive process. Sorry, yes, this additive process. Now, please, I'm moving to the next slide. So if we go for etching, wet chemical etching and dry etching, generally bulk micromachining is done through wet chemical etching. This is very easy process, wet chemical etching. See, just take a beaker, take some solution that is maybe acidic or maybe alkaline or acidic, any type of solution you can take, and put the silicon wafer. Depending on the requirement, the silicon will be etched out. So requirement of the temperature, there is some temperature needed and silicon will be etched out. So that is the bulk micromachining. Obviously, when you are opening this window, this is one window. When you are opening this window actually I am telling about. This window opening, for this window opening, we have to do the photolithography process. We have to follow the photolithography process prior to bulk micromachining process starts. So that is the thing we should maintain in the technology, fabrication technology, microelectronics fabrication technology. So next we are moving to wet chemical etching. Wet chemical etching, two types. One is isotropic etching, another one is anisotropic etching. Anisotropic etching, always some angle is there, maybe 90 degree, maybe 60 degree, maybe 50 degree, right? Here we can see anisotropic etching, the lower one, that is 90 degree steeper structure we have achieved. But the upper one is called anisotropic etching, where, isotropic etching, where we can see the round type of structure, round shaped structure. Isotropic etching, not direction dependent, but an isotropic etching is direction dependent. Particularly when we follow dry etching do the anisotropic etching. But wet etching, wet chemical etching, we can get anisotropic as well as isotropic etching, both. So moving to the next slide. This is the actually structure that is you can see here, anisotropic etching and isotropic etching, and also a three-dimensional picture I have put for better understanding. That is, you can see the V groove. This is called V groove. This is called V groove, and this is called U groove. So V groove and E groove is nothing but if U groove could be extended. If you extend the time, it could be turned into V groove. So V groove and U groove depend all on the requirement. That is how much window you are opening. This is the window actually you are opening. This is the starting window. This is called starting window, and this is the resultant window. The window you are opening, it depends on depending on that, we can understand that whether we will get V groove or we will get U groove. And the thing is that this is a natural process, that if you start with 100 silicon wafer and you will get 54.7 degree angle in the silicon wafer. Okay. If you start with 100 silicon wafer. 100 silicon wafer means that is Miller indices I am telling about, that is HKL. That is H is nothing but 1 by X, K is nothing but 1 by Y, and L is nothing but 1 by Z. So number of atoms present in X-axis, number of atoms present in Y-axis, number of atoms present in Z-axis, obviously silicon atoms I am talking about. So HKL 100, that means there is no silicon atom present in Y-axis, no silicon atom present in Z-axis. Only silicon atoms are present in the X-axis. So 100 type of silicon wafer is called loosely packed. That means number of silicon atoms are less. But if you consider 111 silicon wafer, that means HKL111, that is X-axis, Y-axis, and Z-axis. All are clubbed with the silicon wafer. So this is densely packed. So obviously etching process will be faster if you take some loosely packed silicon wafer, silicon atom, because the etchant can penetrate easily inside the silicon wafer because there are enough space. But if you consider 111 silicon wafer, there is not enough space. So etchant cannot penetrate easily inside the silicon wafer. So if you need faster process of etching, you should take 100 silicon wafer. But if you need a very steeper structure, very accurate structure, then you should go for 111 silicon wafer. So all depends on the requirement and research, based on research actually. So this is the schematic I have put, that is one for pressure sensor, one from gas sensor, that is all are bulk micromachined silicon, and everywhere we can we use this micromachined device, maybe pressure sensor, maybe gas sensor, and many more places also. In IoT, we are using so many sensors, and there are huge application of MEMS technology. So I have already told that what is surface micromachining, but the thing is that surface micromachining is an additive process. I have already mentioned this, that how a cantilever has been fabricated on top of silicon wafer. And one more thing you should learn, that is sacrificial layer. Whatever the material we have deposited, maybe silicon, maybe other else, that is actually dissolving into the etchant, I mean hydrofluoric acid for silicon. So this oxide layer is getting dissolved in the etchant because it is sacrificing itself to make the this micro cantilever. So that's why this is called a sacrificial layer. So there is a stiction problem in surface micromachining. That is, the gap between the micro cantilever and the silicon is very, very less. So if you wash it with water molecule or with any chemicals, if you wash it with any chemical, there is a problem of stiction. That means chemical molecules may get stuck between the structure and the silicon, and it is not so easy task to remove this molecule that is stuck from in between the two layers. It is not so easy tough to remove it. So there are some process, that is critical drying with CO2. That is the process we can remove the molecule inside the trap, from the trap. And also, if we could make the structure stiffer, then there we can avoid the stiction problem. So this is CMOS compatibility, that is CMOS fabricated. You can see particularly the people belong from EC background. This is the structure of CMOS, that is gate drain source. We can see easily, and on the same chip, I mean on the same silicon wafer, the MEMS device has been fabricated. That is sensor, one sensor has been fabricated. So this is the example that we can, I mean, integrate the MEMS with CMOS. That is one of the greatest advantage of CMOS technology or MEMS technology. So another MCQ. So this is a clear picture of bulk micromachining. This is your starting window, that is WO. WO is the starting window. This is the starting window. This one WO, and this is your resultant window. So this is the formula. By applying this formula, we have to calculate how much will be the opening window or the starting window. So WB equals to WO minus 2L cot 54.7 degree. So WB we can calculate in this using this formula, and L is the depth of the bulk micromachine. How much length we will etch out? It will be etched out. That is nothing but the L. And this 54.7 degree is inherited, that is natural process. If you start with 100 silicon wafer, it will obviously etch out with 54.7 degree. No human intervention is there. It is a natural process. So by this way, we can calculate our resultant window. So next is so this is the steeper structure. So I'm not going much deeper. So isotropic etching, I have already mentioned. Choice of etchant is a good factor. What type of etchant should we choose? This is the difference between wet etching, dry etching. First and foremost is dry etching more expensive, wet etching less expensive. And the next process is optical lithography. Lithography process is a very, lengthy process. It takes much time to go through this lithographic process. Before starting the lithography, we should pre-bake the wafer. Pre-bake means just take the wafer, coat it with photoresist. Photoresist is nothing but the carbon polymer compound of carbon, and it is carbon polymerization is there. If you put the photoresist into the oven, this is at roughly 100 degrees centigrade or 200 degrees centigrade. It is called pre-bake. After pre-bake, you have to go through the photolithography process. Photolithography process, it is not so easy to understand if you go through this slide. Still, I am trying to make it easier so that you can understand. That is the gray colored portion is the substrate. On top of that red color portion is the photoresist. And on top of that, this is nothing but this is nothing but the mask. This mask you have to prepare through software, and then you have to collect it from the vendor. And this is obviously just a tensile mask. This is plastic type of material. And see the portion that is blocked, it cannot pass the UV ray. The portion that is open, UV ray can pass through it, and it will soften the photoresist material. And after that, we are getting this one. That is, if we develop this wafer, and if this is positive photoresist, then if we develop, we will get the softened part will dissolved. We will get only hardened part. And if we get negative photoresist, if we are using negative photoresist, the thing is that in negative photoresist, the exposed portion gets hardened. The difference, this is just replica of the positive photoresist. In positive photoresist, the exposed portion, the portion that is exposed to UV ray, it is getting softened. And when we are using negative photoresist, the exposed portion is getting hardened. So if you put the silicon wafer after this exposure into the developer solution, then the softened portion will get dissolved, and we will get this structure. So this is in this way, we can have the structure on top of silicon wafer. This is just an example. And photolithography is called the pattern transfer mechanism. The pattern we want to transfer on the silicon wafer, that can be done only using photolithography. So next is, so UV ray exposure, it is shown. Photo mask is there. This is the example of photo mask. So after photolithography is over, you have to clean the wafer and put inside the oven. This is called hard bake. First one is pre-bake and this is called post-bake. First one is called pre-bake or soft bake. Last one is called post-bake or hard bake. Because why this post-baking is required? Because after developing, there are so many unwanted material, unwanted chemicals might be present on top of silicon wafer that could be removed through this heating. Post-bake is nothing but the heating that could be removed through this heating process. And the chemicals will be waved off. So basically, these two terms is very, very important. One is HVAC, another one is lift-off. The difference between HVAC and lift-off is HVAC is take the silicon wafer, put the silicon dioxide that is green in color, right, light greenish. And on top of that, you put and pattern the photoresist. And if you third step, that is, if you put it into the hydrofluoric acid, the silicon dioxide layer will be dissolved. And now if you put the step 3 silicon wafer inside the acetone solution, acetone is a good agent of photoresist, then photoresist will get dissolved. So finally we get the structure that is mentioned in step 4. So this is called HVAC. Now the lift-off process. Lift-off process just the replica of HVAC. First take the silicon wafer and coat and pattern the photoresist. Then deposit the silicon dioxide layer. And then you put the level 2, I mean step 2 silicon wafer into the HF solution. Not HF solution, in the acetone solution. Acetone is the good agent of photoresist. You can see that it will etch photoresist, and when photoresist will be etched, it will goes off by taking the silicon dioxide layer also, that is green in color. And finally, you are getting the step 4 structure. So if we go to the previous slide, see the HVAC and the next slide, lift-off, is just replica of the structure. So it depends on the requirement. Researcher could understand whether they should go through lift-off process or through HVAC process. So there are so many methods involved with I have shown you the optical photolithography. Not only that, there are so many other photolithography process also. But generally, mostly used photolithography process is optical lithography. So this is the LIGA. LIGA means X-ray lithography, electroplating, and molding. This is the LIGA structure. What is LIGA structure? LIGA structure is high aspect ratio structure. When we are fabricating high aspect ratio structure, then we should go through LIGA process. This is the high aspect ratio structure. You could see the height is much more than the diameter. So this is called LIGA structure, and the process LIGA we follow to fabricate this high aspect ratio structure. Now our device is ready. Now we have to put it on a steady surface, because silicon substrate is very brittle. And if you put it elsewhere, their micro crack generation will be very, very easy, and it will damage the device. It will break the device. So all your effort will be in vain. So you have to place the silicon wafer onto the substrate, I mean stronger substrate. So for stronger substrate, we may take glass, because glass, take a piece of glass or glass slide, put the silicon wafer on top of that. It is not that type of easy process, because it should be bonded properly. The glass and the silicon, it should be bonded properly. For that, we should know what is fusion bonding, what is anodic bonding. For fusion bonding, the process temperature is 1000 degrees centigrade. For anodic bonding, the process temperature is 430 degrees centigrade. For fusion bonding, we actually bond actually complex 3D structures. But when we are bonding the silicon structure on top of the glass substrate, we go for anodic bonding. So silicon to glass bonding is anodic bonding. silicon to silicon bonding is nothing but we follow fusion bonding. So move to the next slide. You can see fusion bonding. See, two silicon wafer has been bonded. Wafers have been bonded. That is how? By this is mechanical process. The silicon wafer is made hydrophilic, not hydrophobic. It is made hydrophilic, and then apply the pressure, and huge pressure is required, and annealing, and then anneal at greater than 1000 degrees centigrade, and now the silicon will bond together. So this bond is nothing but called SiO-Si bond, because first the silicon wafer has been made hydrophilic. Some water molecules are present in between them. So SiO-Si bond is a strong bond. It will not break further. So this is the example of bulk micromachining, micromachined micro pump. Here we can see 4 structures have been bonded through fusion bonding. Next is anodic bonding. We can see that the orange in color or yellow in color is the glass slide, and lower one is silicon. Lower one is silicon. This glass and silicon bonding, for that we need some potential, and this potential we need, and actually this electric field makes it possible to bond between glass and silicon. So the alkali ions, actually Na plus ion, move away from the interface, and in this way, after applying this potential, and now the silicon glass can be bonded. This is nothing but for the rugged structure. To make the structure rugged, we follow the silicon glass bonding through anodic bonding technology. There are some MCQ. Now next the part is thin film sensor. So this is the microfabrication. This is one process animation. You will, we get much more familiar how the fabrication, microelectronic fabrications are going on. Cross-sectional view and top view. This is silicon wafer I have taken. This is silicon dioxide. This is purple in color. Purple in color that is not taken by me. That is not, it is as per my choice, because when you deposit or the silicon dioxide layer on top of silicon, then depending on the thickness of the silicon wafer, the color varies. Actually, when we are taking, say, roughly 0.5 micron thick silicon dioxide layer on top of silicon, then the color will be purple. If we take, say, 0.7 micron silicon dioxide layer on top of silicon, the color will be orange. Then if we take 0.3 micron silicon wafer on top of silicon dioxide layer on top of silicon wafer, then it would be greenish in color. So all depends on the light reflection, because thickness, this light reflection depends on the thickness of the silicon wafer. Number of SiO2, silicon dioxide atoms present in the surface, all are surface phenomena. So after that, this is bulk micromachining. After that, the metallic layer deposited for pattern transfer through photolithography. This is some pattern has been transferred as we are dealing with gas sensor. This is micro heater this pattern has been transferred. Then some sensing layer has been deposited on top of the micro heater structure. So this is the final structure we have got. This is the sensor structure. Now thin film, what is thin film? Theoretically, less than 1 micron is called thin film, but practically less than 1 micron will not serve the purpose. Actually, less than 1 micron, it is roughly less than 500 nanometer could be considered as 500 micron, sorry, less than 500, because 1 micron is 1000 micrometer. 1 micron is 1000 nanometer. 1 micron is 1 micrometer, that is 1000 nanometer. and that is less than 500 nanometer is called practically thin film. So what is thin film? Thin film enhances sensitivity, faster response, annealing temperature is lower, chemically stable. So this is the basic gas sensing mechanism. Due to the natural non-stoichiometry, if you take metal oxide, that is zinc oxide layer, and zinc oxide is not complete. There is a, this is inherited. That is God gifted. There is natural non-stoichiometry present in the metal oxide layer or any deposited material, chemical. This is metal oxide in my case, as we are dealing with gas sensors. So due to this natural non-stoichiometry, the ambience oxygen, that is oxygen present in the atmosphere, is getting absorbed on the surface, because zinc oxide oxygen molecule will try to complete itself by taking the oxygen from the atmosphere. So when oxygen is giving the, making the poor bond with the surface atoms of the sensing layer, oxygen is accepting the electrons from the gas sensor sensing layer surface. That's why it is becoming O minus, and the sensing layer surface is becoming positive. So thus here we can see the poor bond has been established. This bond is called dangling bond. So actually sensing layer surface is the donor and the oxide layer oxygen atom is the acceptor. So this is the donor acceptor relation. So as sensing layer surface is donating the electrons, so less number of electron means resistance is more. That's why we are starting in next slide. We are starting with the high resistance. This is the resistance is higher. But when gas comes, target gas comes, hazardous gas, say for methane, then methane will make the bond with the absorbed oxygen and will make CO2 and H2O and goes off. When the oxygen goes off from the surface of the sensing layer, it will return back the electrons to the sensing layer. As the number of electrons now increased, that's why resistance has been decreased. So resistance is less in this case. So this is the basic characteristics of the gas sensor. So when we are considering resistance, when the resistance is less, the resistance, the gas is present, we can consider. When the resistance is higher, we can consider gas is absent. So this is the basic thing of gas sensor, basic characteristics of gas sensor. Now, here you can see, this is self-explanatory flash player. Silicon, SiO2, then metal oxide. Some absorbed oxygen is there. This is the red color one or orange color one is the target gas, hazardous gas. After, see here, after reacting with the absorbed oxygen with target gas, the electrons, free electrons, will return back to the semiconductor metal oxide layer surface or sensing layer surface, and these all are the byproducts goes off from the surface, that is CO2 and H2. These all are the byproducts. So in this this time the sensor resistance will decrease. So this is one of the structure, and now I am moving to the graphene part, that is hope it is visible. Is it visible? The graphene slide?
Yes, ma'am. Yes, ma'am.
Okay, very good, very good. So, you know what are the function of gas sensor? That is, I am not going to already explained in earlier slide. The performance characteristics, sensitivity, selectivity, response time should be less, sensitivity should be higher, and small size, low power consumption, capability of being wireless. All these are the desired. We desire this type of sensor we should fabricate. So So why graphene? Graphene electrode is better choice for room temperature gas sensor. Earlier, we can see that we have used some metal oxide layer, we have fabricated the gas sensor device, but the problem is that we have to fabricate microheater. Why? Because who will generate the temperature for that gas sensor to activate the sensing layer? That's why we have fabricated the microheater. So the thing is that that sensor was not room temperature gas sensor. Room temperature means 27 degrees centigrade temperature. 27 degrees Celsius temperature, but that gas sensor was operated at 100 degrees Celsius temperature or 200 degrees Celsius temperature. So that temperature could be generated from microheater, but the system has been shifted to graphene. Why? Because this type of microheater, etc., we don't need to fabricate. The fabrication steps has been reduced. It is user friendly also. So if we can fabricate the graphene based room temperature gas sensor, it will be amazing. So why graphene? Because we use graphene because of high carrier mobility, increased specific surface area, low intrinsic noise. Why low intrinsic noise? I don't know. Someone is uh, on mute, I think. Some noise is coming. So graphene, why?
Tuhin Shubro Das sir, kindly mute yourself. Okay, ma'am. Continue. Tuhin Shubro Das sir, please.
Flow of electron. No obstacle is there in the flow of electron. Graphene is such a material. That's why it has got low intrinsic noise. I mean, low obstruction means no scattering is there, no scattering loss. That's why this is low noise device. And pristine graphene, we can see that is the pure graphene is called pristine graphene. Graphene property, if we go to the next slide, then this is the graphene structure, that is honeycomb lattice structure. Carbon atom is arranged in a honeycomb lattice, and the distance between two carbon atom is 0.14 nanometer. So it is two-dimensional honeycomb lattice. When this is three-dimensional honeycomb lattice, we are much familiar with the term that is carbon nanotube. Carbon nanotube and graphene, there is no difference such. The thing is that one is three-dimensional, another one is two-dimensional. So if you go through this structure, you can see that, just a moment. I'm not finding, I'm unable to find the slide. I don't know. So the thing is that, see what is happening. The conduction band, why we should avoid pristine graphene, pure graphene, that is conduction band and valence band in pure graphene touches each other in 6 places, that is called Dirac point. So for that reason, this pristine graphene is not a good match for gas sensor, because we can't manipulate the forbidden energy gap between the valence band and conduction band, because it is already touching each other at 6 different points. So that is the thing we should work with, not graphene, rather than graphene oxide we should work with. Because if we add number of functional groups with graphene, it could be a graphene oxide, and the distance between the forbidden energy gap, that is the distance between the valence band and conduction band, could be increased. So somewhere purity is not the blessing, is the curse that we can see in graphene, that is impurity is the blessing for graphene when we use in gas sensor, because the forbidden energy gap that was not present in the pristine graphene could be introduced by using reduced graphene oxide. So now we can see the different amazing property of graphene material, that is electronic property, high electron mobility, room temperature is 2 lakh centimeters square per volt second, whereas silicon has 1400 centimeters square per volt second. Obviously, silicon 1400 mobility is when we are using p-type silicon. For n-type silicon, the mobility is 2500, 2500 centimeter square per volt second. But we prefer to work with p-type silicon in microfabrication process. Why? Why not silicon of n-type we take? The thing is that n-type silicon means number of electrons are more. So there is a scattering mechanism. Scattering mechanism, one electron bombarded with another electron that is fallen in its path. And scattering means there is a scattering loss. So that is the thing. Scattering means it will generate huge noise. So we should go for p-type silicon, because p-type silicon hole mobility is much less, and the noise production is less in p-type silicon wafer. So this is the electron property is excellent in graphene. Optical property is also excellent. It is not absorbing the light. 97.7% light transmitted from graphene layer. You mind it that graphite and graphene, graphite, say 1000 layer of graphene is called graphite. But when we detach this graphene layer one by one, then up to 9 to 10 layer, we can call it graphene. When it exceeds 10 layer, presence of 10 layer, then we have to call it graphite, because when it is 15 layer of graphene is present, then the characteristics is similar to the bulk graphite. And up to 9 or 10 layer of graphene, the characteristics of graphene is totally different from the graphite. And this property is all we are discussing, that is only applicable when we take these 9 or 10 layers of graphene. I mean 9 or 10 layers of carbon atom. Then we call it graphene. So next is some sensor material could be fabricated. I can show you how easy to fabricate graphene-based sensor. So here you can see there are so many processes involved while fabricating the graphene, and chemical vapor deposition is there, electrochemical exfoliation is there. Electrochemical exfoliation is very easier process, and chemical vapor deposition is a little bit, highly expensive equipments are required. It is costlier process, and also some hazardous process also, because hazardous gases are produced as a byproduct, and some acetylene or methane, some carrier gas is required to fabricate the graphene layer through this process. But the thing is that the graphene layer we are getting through CVD process, that is very, very pure graphene layer. And this electrochemical exfoliation process, the functional oxygen functionalities, many oxygen functionalities are present in the in this graphene. When we are following this electrochemical exfoliation process of graphite. So here you can see the video, and how I will show you later how it is possible to fabricate graphene sitting in our table also by using the Scotch tape method. So this is some of the example of electrochemical exfoliation. I am not going much deeper because this is available in the web also, the process. So thick film and thin film, that is 1 micrometer less than is called thin film, and above 1 micrometer is called thick film. So there are so many processes of depositing thick film, thin film, that is physical vapor deposition process, and also chemical vapor deposition process. These are the technology we are using: physical vacuum evaporation, sputtering, molecular beam epitaxy while doing the following the physical vapor deposition, and chemical vapor deposition also APCVD, LPCVD. This type of, there are many types of chemical vapor deposition, but thermal CVD, that is thermal chemical vapor deposition process, is the most inexpensive setup we require. Else all other is very highly expensive, all other setup. So I am not going much deeper. Physical vapor deposition is nothing but take the metal and put on a filament and heat the filament, and metal will be melted, and then it will be deposited onto the substrate, because there is a heat and metal is getting evaporated and it will be deposited onto the substrate. This is the basic fundamentals of physical vapor deposition. Now the thing is that chemical vapor deposition, there are so many issues involved, that is volatility, stability, reactivity, safety with this chemical vapor deposition process. Here we can see just a moment, chemical vapor deposition. Here we can see how the process is going on. That is, substrate is blue color is the substrate. On top of that, the solid material is deposited. In this case, as we are dealing with graphene, you may consider this as graphene layer on top of silicon, or whatever the substrate material. Substrate material may be silicon and SiO2 also, combined substrate material. So this green and yellow, the layer, we can see that is the solid material, that is may be considered as graphene, or mono layer of carbon atom, multiple layer of carbon atom, because I have already told that up to 9 to 10 layer we can consider it as graphene, 9 to 10 layer of carbon atom. Then this red and violet, this all type of molecule is called precursor molecule. That means the precursor means that is the raw material, that is we are using methane here, say, to deposit the graphene layer. This methane is the raw material in this case. Now you can see how it is happening. The target gas is coming, it is getting deposited onto the substrate, and we can get the graphene layer. Next, again, this is step by step I have mentioned using 3, 4 slides. Step 1, this is step 1. This is step 2, how target gas, after dissociation, the carbon is being deposited and hydrogen is as a byproduct, it goes out from the chamber. This is nothing but the methane or acetylene that contains the carbon atom. That much gas is required that contains the carbon atom. And high temperature is required. That is, chamber temperature should be very, very high, nearly 1000 degrees centigrade or 800 degrees centigrade. It is getting deposited. All are surface phenomena. And after deposition, the resultant byproduct goes off. So here we can see some, here, this is the direct point. I was telling that 6 places carbon in graphene layer, that is valence band and conduction band touches each other. This is the case of pristine graphene. This is the enlarged view. Enlarged view I can show you here. This is the case of pristine graphene. This is the case. This is pristine graphene. This should be avoided until and unless you increase the gap between the valence band and conduction band. You can manipulate the forbidden energy gap. That is the first and foremost criteria of gas sensor, because you have to manipulate the when gas is coming or gas is goes off from the chamber or in the and from the environment, when resistance is decreased, and when the resistance is increased, that is only possible by modulating the forbidden energy gap. When in gas sensor characteristics, I have already shown you that when resistance is decreased, then the forbidden energy gap is less. When resistance is increased, then the forbidden energy gap will be more. In this way, you have to manipulate the forbidden energy gap. That is only possible when graphene is added with some functional nanomaterial. Here it is graphene oxide actually. So this is the case. You see, this is a simple graphene sensor structure. This is simple graphene sensor structure. This is called GFET, that is graphene FET. Just take silicon on top of SiO2, on top of that gold deposited, and two gold contact layer is connected with graphene, and that graphene is working as a channel. Because we know in field effect transistor, channel plays a crucial role. Channel length actually plays a crucial role. So here, this graphene layer acts as a channel. So in this way, we can easily fabricate GFET, graphene FET, and there is a lot of scope of research already done, and there is already future scope also present. Those who are interested to work with on GFET may start their research work. So these are the things. This is new method, and this is actually that thermal CVD setup. You need the source of carbon containing gases and one furnace, high temperature furnace. Just put the wafer on inside the furnace and flow the carbon containing gases, make it available inside the chamber. Carbon will be deposited onto the substrate, and the rest of the byproduct will go off. This is the most simplest setup of graphene deposition. So next is some characterization process are there. This is beyond of the scope of this lecture. So stability study, when we are dealing with some sensor, stability study is very, very important issue, crucial issue, because someday you are getting good stability, someday you are not getting that much of resistance. That is not a good sensor. So if you hold it for 30 days in the same environment, and if the line is straight, then we can call it is a very good stable sensor. So we have to go for the stability study before launching it in the market. So thank you, everybody. These are the books. You may have books in your library. Thank you. Is there any question you may ask?
Yes, ma'am. Thank you. Audience, you are requested, if you have any question, please ask.
Ma'am, myself, Dr. Anubruta Mandal. Ma'am, actually, previous 1 to 2 years ago, actually, I do some laboratory work in the LED. In case of thermal conductivity, some experiment actually work through the graphene. Graphene is used basically in case of thermal conductivity in case of LED. And that time we actually see these all types of properties and that you say in these sessions, and it is very much resourceful, ma'am, for our illumination engineer actually.
Okay, okay. So you have fabricated graphene at that time in your laboratory?
No, ma'am. Actually, my area is actually design purpose, only
Okay,
lighting design.
okay,
But some research scholar and me, just one thing is do the in case of thermal activity. Actually, we use console software.
okay.
Yes, sir.
Software based. Okay.
Yes, 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 ma'am.
Mm-hmm.
Yes.
Who,
Thank you, ma'am.
what is the
Thank
name? What is the name of?
My name is Onubroto Mondal.
Oh, no. Acha, okay, okay.
Actually, in illumination laboratory, we do that. Our my guide is Professor Dr. Kamalika Ghosh, ma'am.
Okay, okay. No. So you have all the method, do the simulation particularly.
Yes, 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 ma'am. Yes,
We have fabricated graphene in our laboratory.
yes, yes,
That
yes,
is the
yes, ma'am.
thing.
Yes,
So
ma'am.
it is very tough to fabricate
Definitely, ma'am.
because
It is very
while
tough, very tough.
very tough, because when you are getting the graphene, this is floated onto the solution. So it is
Yes,
very
yes.
tough to take the graphene from the solution and put it on the silicon substrate because it will break.
Break. Yes, yes, yes. And this
Very
is
tough
very,
job.
very thin, actually.
Very thin. You
Very
can't
thin.
see the graphene layer when it is floating in a water.
Yes, ma'am.
Uh,
Okay, ma'am.
But the etchant
It is.
solution, if with that, okay, please.
Yes, and yeah, actually, this presentation is very, very resourceful for our in case of illumination engineer. Ma'am, if possible, please share at least graphene portions, is if possible. You share
Okay,
actually.
okay,
Yes,
sure.
yes, 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 ma'am. Ma'am, thank you very much, ma'am. Over
Thank
to
you
you,
all of
Rajashri,
you.
sir. Yes,
Yes, sir. Thank you, ma'am. Very much informative and insightful presentation as always. It is nothing to say because we know sir, madam very well from very beginning, from very previously. So ma'am is always helping and very much insightful presentation as always. We are always seen in previous any presentation part also. So this is as per Onubroto sir also, it will be very much helpful for any research scholar and very much resourceful presentation as because that's why it will be very much helpful for others also. So we would like to thank our speaker ma'am, Sunipa madam, as well as our Onubroto sir also. And audience, if you have any query, please ask. And we would like to request our Onubroto sir for presenting the memento for a small token of appreciation for ma'am. This will be sent
sure,
to
sir.
ma'am
Yes.
also. Yes, this will be sent or mailed to madam also. Madam, please accept.
Yes,
Onubroto is
thank you
presenting.
very much.
Yes, ma'am.
Yeah. Thank you very much
Sir,
for,
is it visible, sir?
yes, yes, absolutely.
Yes, yes.
Okay, okay.
Madam, this is for you. Please accept digitally now,
Thank you.
and
I'm
we will mail very
accepting.
shortly. Yes,
Okay.
ma'am.
Thank you very much.
Thank you, ma'am.
Thank you to entire team. Okay. Okay.
Okay,
So
ma'am. Okay, ma'am.
Okay,
Thank you.
ma'am. Okay.
may I leave the session?
Okay. Yes, yes. Yes, ma'am. Yes.
Bye, everybody. If you have any query, you may contact me directly over mail.
Okay, ma'am. I share your mail ID. Actually, some participant that asked to your mail ID. I share your
Which
mail ID.
one, sir? Which one, sir?
Is this your official mail or personal mail, ma'am?
No, no. Official means which one? I mean
Uh,
head or
no, your
GNIT
personal official mail.
GNIT.ac.in, right?
Yes, 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 yes,
Yes,
ma'am.
yes, that much. That I
Yes,
am
yes.
asking about. Okay. Thank you very
Okay.
much. Thank you to all the participants and organizing team and the principal madam of GKC.
Thank you, ma'am.
Bye. Hmm.
Participants are requested to don't leave the session. Actually, our next session will start from 4 p.m. Actually, our first
Yes.
session will not from the 10 a.m. Due to some problem our speaker. So first sessions will held reschedule and that will start from 4 p.m. And I will share feedback link as well as assignment link in live sessions within 1 minute. Rajushi sir, our honorable speaker
Yes,
already
yes,
joined. Ha.
yes, sir.
Sir, please start this session, sir.
Good evening, everyone. Once again, our next speaker, honorable next speaker, Dr. S. Kaliappan sir, has already joined. Sir, can you hear me? Hello, sir. Am I audible?
Yes, sir.
Yes, sir. Audible.
Yes, sir. Kaliappan sir, can you hear me now?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir. We are going to start. Before we start, we are giving small introduce about sir. Dr. S. Kaliappan is a professor in the Department of Mechatronics Engineering at KCG College of Technology, Chennai, where he has been a faculty member since 2023. He completed his PhD at College of Engineering, Gundi, Anna University, Chennai. His postgraduate studies in internal combustion engineering at College of Engineering, Gundi, Anna University, Chennai, and his undergraduate studies at RVS College of Engineering and Technology, Dindigul. He is in teaching profession for more than 25 years. He is recognized supervisor in Anna University in the Department of Mechanical Engineering in the research area thermal engineering, heat transfers, PFD, composite materials, etc. He has served as technical committee head for various conferences and workshops and worked as the reviewers and editorial board member for several national and international journals. He published more than 200 papers in SCI, WS, Scopus Index Journal, around 229 documents indexed in Scopus database with 27 H index and 1947 citations. In Google Scholar, 30H index, 762 I10 index citations of 2522 also. Organized nearly 20 STTP, FDPs, conferences and other technical events also. He holds 15 international Australian patent grants, 14 published Indian patents and 1 Indian patent granted, which signifies his academic credentials. He also authored 20 books, which is being used by the first year to final year students. He is life member in Indian Society for Technical Education, International Association of Engineers, IAENG, a fellow member in Universal Association of Mechanical and Aeronautical Engineers, Institute of Research Engineers and Doctors, the IRED, and also member in Society of Automotive Engineers, SAE India. He got Best Academician Award for the year 2023 from Scientific International Publishing House. He got Young Researcher Award in INSC Awards 2021 for his research work, which he published in the Journal of Applied Fluids Mechanics. He is a member of the doctoral committee in Savita University also. So thank you, sir. We are very much delighted for having you, for being with us, sir. So now stage is yours and you can start your presentation, sir.
Yes, sir. Thank you for your brief introduction about me.
Yes,
So
sir.
before starting my presentation, is it audible, sir?
Yes, sir. Yes, sir.
So good afternoon to all. First of all, I would like to thank management of Greater Kolkata College of Engineering and Management. I thank to Dr. Anburat Mandal, HOD, IQAC coordinator, and also I extend my heartfelt thank to Rajashree Sakrabarti, Assistant Professor in Mechanical Engineering Department, to given this opportunity. So with this word, I will start my presentation. So can you change the co-host to my another login, this login?
Which one, sir?
Yeah, for this.
Yes, sir. Sir, I
Yes,
make
yes,
this, sir.
yes, thank you, thank you.
Yes, sir. It is visible, sir.
My screen is visible, ma'am?
Yes, sir.
Yes. Yes, this is the 5 days online faculty development program in the emerging technology. So my topic is computational fluid dynamics. So myself, Dr. Kaliappan, Professor and Head of the Department of Mechatronics Engineering, KCG College of Technology, Chennai. So this is my outline of the presentation. Introduction, difference between innovative technology and emerging technologies. Characteristics of emerging technology, role of innovation in emerging markets, trending energy, emerging technologies, latest innovation technology, CFD, and then conclusions. Introduction. The process of renewing and modernizing a domain, the product or service by the application of new procedure and introduction of fresh approaches or the establishment of winning concept to generate new value. This is the definition for innovation. The innovation is characterized by the production of value. Both innovative and emerging technologies have potential, but innovative technology actively presents new answers to market problems. Whereas emerging technology are usually only notions that just starting to gain popularity. So this is the difference between innovative and emerging technologies. Difference between innovative technology and emerging technologies. Both have potential, however, emerging technology or new concept gaining acceptance, whereas innovative technology actively presents creative answers to the market difficulties. So this is the main difference between emerging technology and innovative technology, even though those have the potential. This is the main difference. Well, emerging technology may be innovative, but all the innovative technologies are emerging. That is, vice versa is not a true. Innovative technology may refer a novel application of established, widely adopted technology or to enhancement to previously developed or accepted technologies. So this is nothing but innovative technology. But emerging technologies are frequently at the forefront of knowledge, understanding, pushing the limit of what is possible. The link between two is critical to strategize, planning, and investment. So these two will be the main parameter or main thing, that is planning and investment. We take stockholders in the technology sector must identify whether they are working with an incremental advance, that is innovative, or one of has the potential to significantly transform industry or social paradigms. This is emerging. The business and research. The terminology serve diverse function. Innovative technology is frequently a crucial component of continuous improvement plans, whereas emerging technologies may be the part of long-term vision that necessitates increased research and development expenditure. With understanding such as investment carry greater risk and perhaps higher profit. Characteristics of emerging technologies. Curiosity, which rapid development, intelligent, noticeable effect, vulnerability, and vagueness of all the characteristics of emerging technologies. They are the technologies whose research and application areas are still rapidly developing, while their technical and value potential remains largely untapped. These technologies have the ability to change the future battlefield, creating opportunity, but also imposing constraints on conflict. If you take food industry has used emerging technologies as alternative to the pasteurizational, with thermal technologies such as warming heating or non-thermal technologies such as high pressure processing and ultrasound receiving greatest attention. There is no uniformity on what defines a technology as emergent. Although essential characteristics of emerging technologies includes radical originality, relatively fast growth, coherence, conspicuous influence, and uncertainty and ambiguity. The resulting the definition identifies 5 attributes that the future in emergence of novel technologies. One is radical novelty. Second one is relatively fast growth. Third one is coherence. Fourth one is predominant impact. Fifth one is uncertainty and ambiguity. These are the 5 attributes in the emerging technologies. Role of innovation emerging market. Nowadays, the technology driven the solution have the potential to bridge social divides. Emerging markets that establish themselves as innovation hub increases their global competitiveness. Innovative encourages foreign direct investment and forest international collaboration. Role of innovation emerging markets. Driving revenue growth, expanding market reach, scaling operations efficiently, attracting top talent, enhancing competitive positioning. Trending emergency technologies. So these are the various trending emerging technologies. First one is artificial intelligence and machine learning. Second one is quantum computing. Third one is be on the go with mobile trading application, big data analytics, blockchain technologies. These are the trending emerging technologies nowadays. First one is artificial intelligence. So we know very well about that artificial intelligence is a simulation of human intelligence processing by technology, particularly computers. AI application includes expert systems, neural language processing, speech recognition, and machine vision. These abilities work together to do various activities like driving a car or recognizing faces to unlock device screens. So nowadays, instead of putting password in the mobile phone, instead of putting thumb impression in the mobile phone, the facial recognition, that is another emerging technology which is used in the mobile phones. So these will comes under the artificial intelligence. The AI makes use of variety of technologies to enable robots to sense, grasp, plan, act, and learn at human level intelligence. Fundamentally, AI systems detect their surroundings, recognize items, contribute to decision making, solve complex issues, learn from previous experiences, and mimic patterns. The artificial intelligence landscape emphasis of a variety of technologies, including machine learning, neural language processing, computer vision, and others. These cutting-edge technologies enable computers to interpret human language, learn from example, and make predictions. Although each technology evolves on
Hello.
is it audible?
Sir, right now audible. Before that, you are not audible,
Right.
sir.
Okay. Now, sir?
Yes, sir. Yes, sir. Could you repeat, sir, that one?
Yes. This one or
Yes,
this one?
sir.
Next slide.
Yes, sir. Yes,
This
sir.
slide, sir.
Before that.
This one.
Yes.
Okay. These cutting-edge technologies enable computers to interpret human language, learn from examples, and make predictions. Although each technology evolves on its own, when combined with other technologies, data analysis, automation, it has a potential to transform businesses and help them achieve their objectives, such as optimizing supply chains and improving customer service. To begin with the AI system concept, the input in the form of speech, text, and images. These are the input for the AI systems. The system then processes data by applying various rules and algorithms, interpreting, predicting, and acting on the given input data like text, image, and speech. Upon processing, the system provides outcome, that is output, such as success or failure on the data input given. The result is then assessed through the analysis, discovery, and feedback. Lastly, the system uses its assessment to adjust input data, rules, and algorithms and target outcomes. This loop continues till the desired result is achieved. If the desired result is not achieved, again, they revisit the given input and rules and algorithms, revisit and rewrite all the things. Then they are getting the output. Again, they are getting the output which will be manipulated and checked with the desired outcome or desired result. So up to that desired result comes, it will be the repeated. So these are the types of artificial intelligence systems. Artificial intelligence types based on that compatibility, capability, and functionality. Based on the capability, narrow AI, general AI, super AI. Based on that functionality, reactive machines, limited memory, theory, self-aware AI. So these are the how it works AI. These are the key component of the AI. So first step that we are giving the input, that is speech in the form of speech, text, image, context, outcomes. These input which will be processing in the data processing, that is nothing but the rules and algorithms, the interpretation, prediction, and act, which will be in the data processing stage. So from this, the outcome, that is failure or success. Then based on that analysis, discovery and feedback, again, the adjustment which will be done in the form of data, algorithm rules and outcomes. Again, it will be giving us a input. It will be the loop. Key component of AI, machine learning, deep learning, neural networks, neural language processing, computer vision, cognitive computing. These are the various components of AI system. Second, emerging technology, that is machine learning. The machine learning is an AI application that automatically learns and improves from previous set of experiments without the requirement for explicit programming. So there is nothing but machine learning. And next, emerging technology, quantum computing. The drug discovery is one of the practical application of the quantum computing. The quantum computing can assist researchers in better understanding existing medications and developing new drugs to treat diseases such as Alzheimer's and cancers by making it easier to predict protein activity. In contrast to the conventional bit, quantum computing employs the qubit as the fundamental unit of information. The primary feature of this alternative system is that it allows for the concurrent superpositions of ones and zeros, the binary digits that underpin all computing. The quantum computer works using quantum principles. The quantum principles requires entanglement and deep.
Sir, sorry to interrupt. Your voice was cutting again, sir. Hello.
Audible?
Sir, could you please repeat again, sir? Your voice was cutting. That slide, previous one.
Quantum computing. The primary feature
Yes.
of this alternative is that it allows concurrent superpositions of ones and zeros and binary digits that underpin all computing. A quantum computer works using quantum principles. The quantum principles requires a new dictionary of terms to be fully understood. Terms that include superpositions, entanglement, and decoherence. Next one is mobile trading application. The mobile trading application is use of smartphone to conduct stock market transactions. It is more complex than traditional computer-based trading, as well as faster and easier to use. A user can purchase and sell stocks as well as monitor his portfolio on his mobile phone using variety of applications. Next one is big data analytics. Big data analytics refers to the methodologies, tools, and applications used to collect, process, and extract insights from large, high-volume data sets. These data sets could come from variety of sources, including web, mobile, email, social media, and networked smart devices. Big data analysis, this is the things we are having in that one. That is volume of data, that is set of data which will be collected. Whereas if, for example, velocity, that should be the speed at which data is generated. Variety, the different data types of data which will be collected. Veracity, that is data accuracy. Value, that is useful data. Validity, the outcome which will be data quality, governance, master data management are massive. Variability, dynamic evolving behavior in data source. Venues, distributed heterogeneous data from multiple platforms. Vocabularies, data models, semantics that describes the data structures, variabilities, confusions over meaning of big data and tools used. The last emerging technologies, blockchain technology. The blockchain is defined as a distributed database that maintains a continuously growing list of ordered records known as blocks. These blocks are linked using encryptions. Each block includes cryptography, hash of the proceedings block, and time span and transaction data. So this is the schematic diagram for the blockchain technologies. Next, we can see about that latest innovation in technologies. So these are the various technologies nowadays they are using. VR, that is virtual reality. AR, augmented reality. IoT, Internet of Things in smart cities. Biotechnology in agriculture industries. Autonomous vehicles in automobile industries. Computational fluid dynamics common for all the areas. Virtual reality. Unlike the first generation PlayStation of VR, which recorded player motions with an external PlayStation camera and PS, VR2 uses 4 cameras in front of headset. Despite virtual reality being initially marketed to us gaming application, there are many potential and existing VR applications in various sectors, field, including education, training, simulation, and even in exercise and healthcare application. Next one is augmented reality. Augmented reality enhances your surroundings by incorporating digital components into live view, typically useful using a smartphone cameras. VR is a fully immersive experience that replaces the real world with simulated one. For example, if you wear that augmented reality, if you want to see the zoo, which is in the somewhere very far away place, that will be coming into the pictures as real world in front of us. So this is the augmented reality, how it is working. Schematic diagram which will be explained various parameters and various things. Next one is Internet of IoT. Internet of Things, IoT in smart cities. Automation and control. The IoT provides seamless automation and control of many components of a home and its applications, including switch on that light, heating the rooms, security systems, there is CCTV, and entertainment devices like TV and other things. A technology advances, the future of IoT smart cities is full of existing opportunities. Increased connection, AI integration, 5G network deployment, and public participation are just few of the trends and predictions that will impact the future of smart cities development. So this diagram shows the various application of IoT in various field. If you see the first diagram, it will be tell about that traffic system and monitoring air quality. And second diagram, which will be indicating that public safety solutions. Third diagram, which will be intimating the smart lighting and smart waste collections. Next technology, biotechnology in agriculture. The technology advances, the future of IoT smart cities is full of existing opportunity, increased connections, AI integration, 5G deployment, and which will be used in the various agricultural sectors. This is a biotechnology agriculture. This diagram will show the everything. The disease-free plant participation costs, reproduction of in aquacultures, pest resistance costs, biofuels, enzymes, fermentation, and improved yield. So these are the various things which will be involved in. Next technology, which will be automobile sectors, that is autonomous vehicles. They reduce the traffic congestions 30%, fewer car on the road. Reduce transportation cost by 40%, including vehicles, fuels, and infrastructures. Enhance walkability, livability. Open up parking lots for other purposes like schools, parks, community centers. The autonomous vehicles use remote sensing technology such as radar, GPS, cameras, and lidars to monitor and produce 3D map of their surroundings. This environment often consists of street infrastructures, other vehicles, pedestrians, traffic light, and road signage. This is autonomous vehicles, which will be what are the things which we are using in that autonomous vehicles technologies. How that automated vehicles which will be working interrelated with all these parameters, that is cameras, lidars, radar, GPS unit. And last, innovative technology, computational fluid dynamics. The CFD allows engineers to precise anticipate fluid dynamics such as pressure, temperature, velocity, and turbulence in complicated system or process that would be hard to examine using traditional testing methods. So wherever the traditional testing methods which will be fails to check, in that case the CFD which will be the main tool which will be the used. The CFD simulation services are vital tool in a variety of sectors. CFD, which serves a variety of sectors, which will be given in that diagram, how it will be indicated. Application of CFD in course of my endeavor. So I taken that CFD concept in my research work. How the CFD concept which will be used in my research field to understand, to infer, to optimize any component working on fluid dynamics, which will be associated with the heat and mass transfer. We have three different approaches. In the CFD, we have three different approaches. One is experimental fluid dynamics. Second one is theoretical fluid dynamics. Third one is computational fluid dynamics. So from these three approaches, I taken computational fluid dynamics approach for my research work. So why we need to check CFD? Why we need select CFD, or how these three which will be validation are validated? If you take first method, first approach, it will be the costlier one. It is time consuming, single purposed. We cannot use for multi-purpose. Loss of insights, loss of foresights, error during measurements and instrument errors. For example, wind tunnel testing of a car. Second method, second approach, theoretical fluid dynamics. It will give the accurate result. It will give the results which are continuous, tough to generate and solve, meant for simple physics and simple geometrics. Many assumptions and approximations we are putting in that analysis or in that approach. Best example for this, one-dimensional heat conduction equation, wave equations. Third method, computational fluid dynamics, and alternate with overcoming all the difficulties which is faced other two approaches. Approximate these solutions which will be again approximate. The results are discrete. It is not continuous result. It is a discrete. Needs to expertise in application. So these are the differences between these three approaches. Computational modeling is nothing but combination of mathematical equation and experiment. So if we arrive any problem, for that problem we have to write the mathematical equation. For that mathematical equation to validate, we need to conduct various experiments. If we can combine these two, we can get computational methods. The different quotients present in the mathematical equations are converted into different quotients. The discretized form of equations are solved in millions of nodal points to obtain piecewise continuous set of solutions. It involves major activities. First activity, pre-processing. The pre-processing, which involves geometric domain, type of flow, define and computational fluid domain, and check for predominant flow direction and mesh generation. These activities which will be comes under the pre-processing activity or pre-processing stage. Second stage, solver. The solver involves by selecting the suitable flow model, giving the various input parameters like velocity, temperature, pressure, and fluid properties, and interaction that is calculations they have been made and run to check the convergence principles. This will be comes under the solver activity. At last, the post-processing. After doing all the iterations based on the given input, the outcome, that output which will be given in the post-processing activities or post-processing stage. Post-processing is important to check the residuals, relative solution changes, and contours to make sure that interactions coverage. Solution of derived quantities like stream function, vertices, and also solution parameters like lift, drag, total mass, mass weighted average, etc. And 3D information. It will be showing cut lines, diagrams, cut plates, iso surface, iso volume. So in my research, first I created a CAD modeling. That is 3D modeling is drafted by using SolidWorks software. That is, first I drawn a 2D diagram, then that will be converted into 3D modeling. After creating that 3D modeling, surface and volume discretization, the surface cleanup and CFD domain extraction and surface meshing are done in the ANSA software. Different types of elements like tri, quad are approximately used to define the non-conformal interfaces which facilitate motion of intake and exhaust valves. So this diagram which indicating the inlet section, outlet section, and intake and exhaust valves in the surface and volume diagram. So in my case, I create a dynamic meshing. So when the flow analysis which will be runs, the mesh which will be moving from top to bottom, again it will be moving from bottom to top. So that will be call it as dynamic meshing. So that will be given the output like this. For this dynamic mesh, these are the governing equations which is used. Conservation of mass equation, conservation of energy equation, conservation of X momentum, transport equations, K epsilon, turbulence model. Conservation of mass equation, that is nothing but the mass which is entering and leaving, which will be same. Conservation of energy, again, the energy which will be given as input and exit, both will be the same. Conservation of X momentum, Y momentum, and Z momentum. From this X momentum, I taken for this one, and transport equation, various turbulent models we are having. From that K epsilon ring model, I taken for my solution. For this various boundary conditions, I assumed air is assumed as a continuum fluid. Pressure inlet boundary conditions are input with 1 atmosphere total pressure. Pressure outlet boundary condition, which is also 1 atmosphere static pressure. Walls are assumed as a adiabatic with no slip conditions. Piston motion is controlled by UDF function, user-defined functions. Wall movement are included by transient profile, that is dynamic meshing. These are the boundary conditions I given for the research. That is inlet P total, which will be 0. Outlet pressure, static pressure, which is 0. Outer walls, that should be thermal conductivity. Pistons, which will be adiabatic. Moving walls, motion is governed by user-defined function. Walls adiabatic, moving walls motion is governed by the wall profile diagram. This is the outcome for the inlet valve profile and outlet valve profile. The crank angle versus intake valve lift and crank angle versus exhaust valve intake. For this analysis, we have to validate our output with the given input. That is called validation study. Here, the validation study, that is nothing but finding the optimal mesh count, right turbulent model, and correct discretization. These are the three parameters which will be involved in validating the study, validation study. That is optimum mesh count, turbulent model, and discretization. One implements model into computer code, then uses code to perform CFD simulation, which yields value used in engineering analysis. Validation examines the error in the code or simulation outcome. While we are doing kind of trial and error analysis, comparing each and every CFD results with experimental results to find the best way of discrepancy between CFD and experimental result varies. So first we are taking base readings from the experimental setup and we are doing the CFD analysis and we are getting the outcome. We are comparing with the experimental results and CFD analysis. If a results which will be matching, then our CFD analysis results which will be okay. That will be validated. So for this, we taken three studies. One is grid independent study, which will be giving the how much mesh we have to generate for the given model. That will be grid independent study. Turbulent model, various turbulent model we are having, from that which turbulent model we have to select, and order of discretization study. These are the three things we are doing in that one. First one is grid independent study. It performs or eliminate or reduce the influence of number of grid or grid size and the computational results. When you solve any CFD problem, the solution should be and should not be affected by the size of your given grid or mesh size. This study made for accuracy of CFD solution and to keep the computational cost low. The grid independence test, from this test the mesh which will be generated 96,760 element and experimental results which will be 4,70,744 element were meshed to achieve the experimental results. For this, we started with 96,730 element and which will be calculated, rechecked and reframed that grid size and mesh count, which will be increased up to 4,70,744 elements. So each time mesh was checked and increased by 1.5 times of the value to increase the accuracy of the result. The results for validation study: pressure theta, P theta curve is used to compare CFD results against experimental results. Second, turbulent model. David Carson, the director of program manager, Alter mentioned, until there is a single model of turbulent developed, CFD engineers will always be faced with the challenge of selecting the right model for the right problem. And another scientist, CD Group and NC Marketers studies, Imperial College London 2019, had studied and the importance of all an evaluation and turbulent model for numerical study in cylinder flows. Several turbulent models were studied to compare the effect of turbulent modeling in cylinder flows. These two scientists concept which will be implemented in our turbulent model studies. So here high Reynolds number model and low Reynolds number model. These two which will be taken and counted and re-examined, everything which will be done based on the turbulent model studies. These are the validation 3 studies. So grid independent study, from that the 3,96,525, the difference of deviation from the experimental and CFD result deviation which will be coincide 6.98 and 6.80. So we taken that 3,96,525, that is concurrence which will be acted between 3,96,000 and 4,70,000 as a 6.98, 6.8%. And second study, turbulent model selection. So here RMG K epsilon model which will be selected. And selection of order of discretization. Here second order discretization scheme which will be used to accurate results. To study this trapezoidal profile, we had turbulent intensity, swell, and tumble concept. These flow parameters which will be taken in cylinder physics. The entire in cylinder physics is dominated by 3 parameters: turbulent intensity, swell, and tumble ratio. Swell and tumble enhances acceleration of mixing of fuel and air, and swell promotes a rapid combustion. And turbulent intensity is the main measures that stabilizes ignition parameter process, and higher its value assures faster propagation of flame. Important of swell, tumble, and turbulent intensity. Swell ratio and tumble ratio are 2 important measures that characterize the level of turbulence in engine flow, and definition of these 2 parameters which will be very, very important parameters. This is the various results which is taken from the sinusoidal velocity nature and the trapezoidal velocity nature. Actually, here I want to say one thing. In the existing internal combustion engine, the flow propagation model which will be sinusoidal velocity profile. For my research, it will be trapezoidal nature of velocity profile I taken for my consideration. I compared with the trapezoidal velocity profile with the sinusoidal velocity profile. For this, I taken 4 different model. Model 1, 2, 3, 4. 4 different model. I compared with the various model values and the velocity ratios and pressure and temperature ratios. From this model 2, which will be given that optimal model, compare with the sinusoidal model. This is another graph which is taken at 180-degree crank angle of swell as well as developed starts to stabilize. So again, in this case also, result which is coincide with the sinusoidal velocity profile. And another one which is taken at 350-degree crank angle. So here also the model 2 which will be the coincide with the sinusoidal nature of velocities. This is the tumble ratio and swell analysis for various modules for the sinusoidal as well as trapezoidal nature. This graph which will be indicating model 1. This will be indicating the model 3. This will be indicating the model 4 value. This will be the optimum solution obtained model 2. So from all these analysis, this is the conclusions I arrived for my research work. The CFD are conducted for 4 different trapezoidal configurations with 4 different models, and results are compared with the sinusoidal velocity profile. Comparing all these 4 models, 4 different categories, trapezoidal configurations, the 26 teeth in internal gears and 18 teeth in pinion is found the optimum solution given compared with the sinusoidal profile. The percentage of variation of swell-temple ratio from sinusoidal profile, which will be nearer to this ratio. This is the model 1, model 2, model 4, and model 2. Swell ratio 4.1, temple ratio 3.7, which will be given nearer value with the sinusoidal nature of velocity. Thank you. Yes, sir. Is there any queries?
Sir. Audience, if you have any query, you can ask.
Rajesh sir, I am present. I am sharing the cell mementos. Okay, sir?
Okay, sir. No issue.
Yes, sir. Any queries, sir?
Yes, anybody, if you have any query, please ask. That is there. And I must say that as always, this presentation also very much nice and very much informative, as the audience were, many of them were telling in the chat box also till now. And somebody was asking about the PPT also, sir.
Yes, sir.
Okay,
I
sir.
will share. I will share now.
Yes. So if you can mail us, we can share with the audience or with the participant.
I will
Okay.
share with you, sir. You can share with the participants. No issue.
Okay, sir. I will request Anubroto sir, our convener, and HOD electrical and IQAC coordinator, sir, to share the memento for Kaliappan sir. This will be the, yes, small token of
Sir,
appreciation,
is
sir,
it
for
visible,
our
sir?
end.
Sir, is it visible?
Yes, ma'am. Yes, ma'am.
Okay.
Thank you, ma'am.
Sir, this is for you. Please accept.
Yes, sir. Yes, sir.
And we will mail you shortly by our convener, sir.
Yes, sir.
Thank you, sir.
Thank you. Thank you very much. Once again, I thank Rajasri Sakravati sir for giving these opportunities. Thank you for all the participants patiently listen my presentation. Thank you, sir.
Thank you once again, sir, for your informative presentation. And all the participants are requested to fill up the attendance as well as the assignment and feedback link already shared in the chat box in the WhatsApp group also. And today we are ending our session here, and tomorrow we'll be meeting again by 10 a.m. with the schedule that we have shared previously. Thank you all, and we are ending our session here. Thank you, Anubroto sir. Thank you, Raghunath sir.
Thank you.
Yes, sir. And thank you, Subhasis sir also. He is also doing our good job
Thank you, sir.
from the back end. Yes, from the back end by YouTube Live. Thank you all the team members. Thank you.
Thank you, sir.